It began quietly, like most big discoveries do, a small alert on a telescope feed, a streak of light moving across the dark sky just a little too fast. Astronomers see moving dots all the time. Most turn out to be routine, asteroids, comets, maybe a satellite playing tag with sunlight. But this one refused to behave. Its speed was wrong. Its angle was wrong. And within hours, the numbers told a story that sent a ripple through every observatory paying attention. This thing didn't belong here. They called it 3I Atlas. 3I because it's only the third confirmed interstellar object ever found, and Atlas for the Hawaiian telescope that first spotted it. The name sounds clinical, but what it represents is anything but. It's a rock, or a ball of ice and dust that has traveled for millions, maybe billions, of years between the stars, flying blind through the galaxy until it stumbled into our solar system by chance. And now it's cutting through our backyard like a cosmic tourist who didn't bother to check the map. In astronomy, interstellar isn't just a cool word, it's a badge of origin. Most comets and asteroids loop around our sun, bound by gravity like bees circling a hive. Interstellar objects, though, don't orbit. They pass through. Their trajectories are hyperbolic, open-ended. They enter fast, swing around the sun, and leave even faster, never to return. The math says that once you're moving above a certain speed, about 42 kilometers per second relative to the sun, you're gone forever. Atlas cleared that bar easily. It's not from around here, and it's not staying. Imagine that for a second. Something from another star system. Maybe from a world with its own planets, its own comets, its own suns rising and setting in alien skies, just wandered into ours. It's the astronomical equivalent of finding a message in a bottle, drifting across an ocean so vast that no one ever expected mail to come through it. What made this one even stranger was its tail. Normally, a comet's tail points away from the sun, blown outward by solar wind, a stream of charged particles constantly blasting through space. But when astronomers took a closer look at Atlas, its tail seemed to be pointing toward the sun. That shouldn't be possible. It's like watching smoke flow into a fire. The data looked like nature had decided to break one of its own rules, and the scientists were left blinking at their screens, wondering if their software had glitched or if the universe had. There's a reason astronomers get excited about these visitors. Every interstellar object is a physical sample from a completely different solar system, a fragment of a star's ancient construction site. Whatever it's made of, it carries chemistry we've never touched. Materials shaped by alien suns and frozen for eons in the cold dark between stars. That's not poetry. That's literal. It's like finding a meteorite that's not just from another planet, but from another galaxy of planets. And unlike most space mysteries, this one is happening right now. As you hear this, Atlas is somewhere out there, a faint dot of light rushing through the inner solar system, bright enough for big telescopes to catch it, fast enough that it'll be gone soon. Astronomers are scrambling too. Collect as much data as possible before it slips back into the endless dark. They know this is a one-time encounter. Once it's gone, it's gone. There's something humbling about that. Humanity builds billion-dollar telescopes, hurls satellites across planets, and still, sometimes, all we can do is point our cameras at a moving speck and whisper, "What are you?" We don't get to stop it. We don't get to visit it. All we can do is watch, measure, and imagine. The universe doesn't owe us explanations, but it does drop hints. And every so often, one of those hints drifts in from another star, flashing for just a moment before it's lost forever. That's 3I Atlas, a quiet reminder that while we think we know our neighborhood, the cosmos still has visitors we never invited and stories we haven't yet learned to read. The stranger has arrived, and it's already on its way out. When scientists ran the first orbital simulations for 3I Atlas, the computers practically laughed. The path didn't curve in a familiar ellipse. It didn't circle back like the lazy loops of our homegrown comets. It just kept going. The line on the screen bent once, a sharp turn near the sun, and then shot back out into deep space, never to return. It wasn't a loop at all. It was a flyby. That one shape, that simple curve, told the whole story. This thing wasn't born here. It wasn't part of the sun's family. It came from somewhere far beyond the invisible fence that holds our planets in place. It had broken every rule of local membership. To understand why that's so strange, you need to know how tightly our solar system normally keeps its secrets. The sun's gravity is a bossy landlord. Everything that forms here stays here, orbiting in predictable patterns. Even comets that come from the distant Oort cloud, that frozen shell of leftovers at the solar system's edge, are still bound to the sun. They may wander for centuries, but eventually they come home. Atlas doesn't. Its orbit isn't bound at all. It's what astronomers call hyperbolic, meaning its speed is so great that even the sun, the heavyweight champion of gravity, can't pull it back. It's the celestial version of skipping a rock that never lands. It just keeps moving forever. When the data first came in, some astronomers thought there must be a mistake. Maybe the measurements were off. Maybe the angle was miscalculated. But the numbers held. The object's velocity was too high, its trajectory too open. It wasn't one of ours. Think of it this way. Most comets are like kids on a playground merry-go-round. They speed up near the center, slow down as they move away, but they always come back around again. Atlas is the kid who grabbed the edge, kicked off, and launched himself straight into the parking lot. So what could fling an object out of its home system with that kind of power? Probably chaos, the kind that happens when giant planets fight over gravity. In young solar systems, newly formed worlds jostle for space like toddlers fighting over toys. One planet nudges a comet just a little too hard, and suddenly it's sailing into the void at interstellar speeds. For millions of years, it drifts in darkness until, by sheer chance, it crosses paths with another star, ours. This randomness is one of the strangest truths in astronomy. Space looks calm, but it's built on accidents. The same chaotic gravitational ballet that may have thrown Atlas out of its home could have also created us. Our solar system's own early years were a demolition derby of collisions and near misses. Earth itself was nearly destroyed before it became stable enough for life. When you zoom out far enough, order and chaos start to look suspiciously alike. What makes 3I Atlas special is that it's living evidence of that chaos. A souvenir from a system that isn't ours. The atoms in it were born around another star, maybe one smaller and redder than the sun, maybe one that's already dead. It's a frozen relic from a time and place we'll never visit, and yet, by a twist of geometry and gravity, it's here now, brushing past our cosmic doorstep. Astronomers can tell a lot from that shape, the hyperbola, the sharp curve near the sun. The closer the object passes to the sun, the more it accelerates. In Atlas's case, it's been clocked at speeds exceeding 100,000 kilometers per hour. At that pace, it could travel from Earth to the moon in under 4 hours. It's not speeding up because of engines or mystery forces. It's just gravity doing what gravity does, converting distance into motion like a slingshot made of sunlight. For context, every planet in our solar system, even fast Mercury, follows a neat, predictable ellipse. Kepler's laws, Newton's math, all the comfortable machinery of classical physics work perfectly on them. Atlas is a reminder that not everything in the universe reads the manual. You can almost feel the tension in the scientific community. On one hand, it's thrilling, a real piece of another world drifting through ours. On the other, it's infuriating. You can't send a probe fast enough to reach it. You can't steer it. You barely get a few months of observation before it's gone. Studying something like this is like trying to analyze a snowflake as it melts in your hand. But that fleeting nature is part of what makes it meaningful. It's a momentary hole in the fabric of normality, a reminder that the laws we take for granted are just local customs, not universal truths. Out there, beyond the sun's reach, gravity, chemistry, even sunlight play by different rules, and every once in a while something crosses the border to show us. Astronomers like to talk about reference frames, points of view, and motion. To Atlas, we're the ones moving. Our entire solar system is racing around the Milky Way at 800,000 kilometers per hour, dragging all its planets, moons, and leftover debris along for the ride. So when something like Atlas passes through, it's not just visiting, it's part of the galactic traffic, a traveler from another lane on the cosmic highway. When it's gone, its trajectory will carry it out towards some unknown corner of the galaxy, maybe into another star system millions of years from now. There, someone else might see a faint streak in their sky and wonder, what is that? They'll run the math, realize it doesn't belong, and maybe they'll call it 4I/something, another interstellar visitor breaking the rules all over again. That's the beauty of it. These are the rarest objects in astronomy, the ones that don't just orbit, but wander. And for a few short months, one of them has crossed paths with us, showing that the universe still plays by rules we haven't written yet. The solar system has laws. The universe doesn't always obey them. When people picture a comet, they imagine the classic postcard version, a glowing white core, a long, elegant tail sweeping out into space, and that tail always stretching away from the sun. It's one of nature's most consistent signatures. Sunlight and solar wind push dust and gas outward, forming that bright backward plume. It's predictable, almost polite. A comet bows to the sun and trails its scarf behind it. Then came 3I Atlas, which apparently didn't get the memo. When the first images of its tail hit astronomers' screens, there was a collective double take. The tail didn't seem to be pointing away from the sun. It looked like it was reaching toward it. That's like watching smoke drift into a fire or a windsock blow against the wind. It shouldn't happen. Not with the known laws of radiation pressure, not with the standard models of dust and ion tails. At first, the community did what scientists always do when something breaks the rules. They blamed the instruments. Maybe the telescope's angle was off. Maybe there was image noise. Maybe someone sneezed during the exposure. But no matter how many observatories checked, the tail stayed defiant, angled toward the very thing that should be blowing it away. So what's going on? The short answer is physics, but weird physics. Comet tails aren't actually one thing, they're two. The first is the dust tail, fine particles pushed away from the nucleus by sunlight. The second is the ion tail, made of electrically charged gas molecules that respond not to light, but to the sun's magnetic field carried by the solar wind. Usually, these tails more or less align, both pointing away. But if a comet is coming in at a strange angle, or if the magnetic field lines twist unpredictably, the ion tail can appear to bend in the wrong direction. That's what may have happened with Atlas. The sun's magnetic field is a sprawling, rotating mess. It reverses polarity every 11 years and flings invisible arcs of charged particles in every direction. If the comet wandered into one of those warped regions, the magnetic field could have grabbed its ion tail and yanked it sideways, or even inward, relative to the sun. Still, the way it happened was extreme. Some astronomers think Atlas might have an unusually strong magnetic response. Perhaps it's rich in metals or exotic ions that interact differently with solar plasma. Others suggest it could be a trick of perspective. We're seeing the tail from a certain angle that makes it look reversed. But even then, the data shows something genuinely odd in the particle flow. A hint that this object doesn't just come from another star system, but another magnetic environment. That's a subtle but mind-blowing idea. Every star in the galaxy has its own space weather, its own version of solar wind, shaped by its size, rotation, and activity. The chemistry and magnetism of Atlas were sculpted by a completely different star, maybe one that flared harder or spun faster than ours. When those ancient ices and metals meet our solar wind, they behave in ways that our local physics doesn't fully predict. It's like mixing ingredients from two recipes that were never meant to share a kitchen. The result? Chaos, light, and confusion, the three pillars of good science. The beauty of this kind of anomaly is that it forces people to look twice at what they thought they understood. Comets have been studied for centuries. We know their dance moves. We've landed probes on them, smashed impactors into them, analyzed their dust. But one weird interstellar guest can flip that confidence on its head. It's humbling and exciting, when nature reminds us we don't have the full story. A comet's tail isn't just pretty, it's a message. It tells us about temperature, solar radiation, particle density, magnetic interference. It's a diagnostic light show, and with 3-eye atlas, the show just got unpredictable. For a few months, the comet's reverse tail became a kind of cosmic meme in the astronomy world. Amateur observers tried photographing it, professional researchers published frantic preprints, and the public mostly ignored it, which frankly is fine. The universe doesn't care whether we're watching, but for those who were, it felt like a front row seat to a physics lesson written in fire and ice. There's something poetic about that image, a comet that seems to defy the sun, racing past it with its tail flipped like a rebellious flag. But under that poetry sits a real scientific challenge. Every time we see an exception to the rule, it tells us there's a deeper rule waiting underneath. Maybe Atlas's chemistry reacts differently to ultraviolet light. Maybe its dust grains are larger or denser than expected. Maybe, and this is the dream scenario, its materials are unknown in our solar system entirely. If that last one turns out true, it means we're literally seeing matter that formed under different stellar physics, an alien fingerprint in our sky. As Atlas continues its sprint around the sun, it's shedding that material into space. Dust, gas, ions, a faint ribbon of alien debris we'll never touch but can still measure. Even after it leaves, the data will linger. Light curves, spectroscopic lines, magnetic readings. Clues to a chemistry we didn't invent, from a place we've never seen. And maybe, just maybe, the next interstellar visitor will make even less sense. Before 3-eye Atlas came screaming through our corner of space, there was another visitor, the first one we ever caught in the act. Its name was Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and it lived up to the name perfectly. Discovered in October 2017, Oumuamua was the first confirmed interstellar object ever detected. Before that, the idea was mostly theory. Astronomers had long suspected that other stars' debris must occasionally drift into our solar system, but we had never seen proof. Then, Oumuamua showed up, broke every expectation we had, and vanished before we could figure it out. Imagine spotting a strange car speeding down your street, but it's going 100 miles an hour and doesn't stop. You get one blurry photo, and it's already halfway to the next town. That's basically what happened. Oumuamua came in fast, around 87 kilometers per second, and on a hyperbolic trajectory that made it instantly clear. Not local, not bound to our sun, not one of ours. The timing was perfect, too. The Pan-STARRS telescope in Hawaii had just gotten a boost in its detection capabilities, and someone noticed a faint cigar-shaped speck moving just a bit too oddly. Within days, the world's telescopes pivoted to get a look before it disappeared, and that's when things got weird. Unlike a typical comet, Oumuamua didn't have a visible tail. No gas, no dust, no coma. Just a tumbling, reflective rock about 400 meters long. It wasn't shaped like anything we'd seen before. Most asteroids are roughly spherical or potato-shaped, but this one was elongated. Some models suggested up to 10 times longer than it was wide. Then came the stranger part. It accelerated. After slingshotting around the sun, Oumuamua began to move slightly faster than gravity alone could explain. Not by much, just a few meters per second, but enough to raise every eyebrow in the field. Normally, that would be due to gas jets from sublimating ice, but there was no visible gas, nothing to push it. Cue the conspiracy machine. Some scientists floated cautious theories. Maybe it was an unusual, low-density body shedding invisible hydrogen. Maybe its surface was covered in reflective materials that heated unevenly. And then a few brave or reckless voices said the quiet part out loud. What if it's artificial? The media, naturally, lost its mind. Harvard astronomer Avi Loeb published a paper suggesting Oumuamua might be a piece of alien technology, perhaps a discarded probe, a solar sail, or some fragment of an ancient machine drifting through space. It wasn't a claim of aliens per se, but it was close enough to spark headlines and angry emails. Most scientists disagreed, pointing out that extraordinary claims need extraordinary evidence, and there just wasn't enough of it. Oumuamua's behavior could still be explained by natural processes. Weird ones, sure, but natural. Still, that didn't stop the speculation. When something breaks every rule you thought you knew, your imagination fills in the blanks whether you like it or not. The truth is, Oumuamua was probably just weird. A shard of rock or ice ejected from a distant system, battered by cosmic radiation until it took on its strange shape and shiny surface. But probably isn't very satisfying in science. It's like getting a riddle with the last clue missing and knowing you'll never find it. Because by the time the world noticed Oumuamua, it was already leaving. No mission could catch it. No telescope could resolve its fine details. It was here for weeks, then gone forever. Its closest approach to Earth was just 24 million kilometers, and then it was off, fading into the black. But that one encounter changed everything. It proved that interstellar objects do wander through our solar system. It forced agencies like NASA and ESA to consider building ready-to-launch interception probes for the next time it happens. And it reminded astronomers that space isn't a closed system. It's a crossroads. Fast forward a few years, and 3I Atlas arrives, the third known visitor, but the first with a visible tail. Unlike Oumuamua, this one looks more like what we expect. Icy, gassy, comet-like. But that only makes the contrast sharper. If Oumuamua was the mystery novel, Atlas is the sequel that starts filling in the clues. Both share the same origin story. Exiled fragments from alien solar systems, ejected by gravitational chaos, drifting through the galaxy until luck brought them here. But Atlas is giving us what Oumuamua couldn't: real-time data, spectroscopy, chemistry. Proof that these objects aren't myths or anomalies. They're part of a larger population we're just beginning to detect. Astronomers now estimate that trillions of interstellar objects may be drifting through the Milky Way at any given time. Most are tiny, dark, and invisible. But every so often, one happens to cross Earth's orbital path. And if our instruments are watching at the right moment, we get a brief glimpse into another solar system's history. Oumuamua was our first glimpse. Atlas is the next. And with new observatories like the Vera Rubin telescope coming online soon, we might start seeing these visitors not once a decade, but once a year. Each one will tell a different story about how other systems form, live, rise, and die. But for now, 3I Atlas is the one in our sky, the new messenger, the sequel to a mystery that began with a cigar-shaped ghost and 1,000 unanswered questions. And if Oumuamua taught us anything, it's this. Every time we think we've seen everything the cosmos can throw at us, it proves us wrong in ways that make our telescopes feel small and our curiosity infinite. When you hear that scientists know what a comet or star is made of, you might picture someone scooping up a sample, running it through a lab, and nodding wisely over a microscope. But in reality, most of what we know about the universe comes from light, a few photons that have traveled for millions of years, carrying secrets hidden in the way they vibrate. That's not poetic exaggeration. That's literally the job description for a field called spectroscopy, the science of reading the chemical fingerprints of light. And when 3I Atlas appeared, that's the first thing astronomers reached for. Not a net, not a rocket, but a prism. Here's how it works. When light passes through gas or reflects off matter, it carries a record of what it touched. Each element absorbs and emits light at very specific wavelengths, forming a pattern of bright and dark lines known as a spectrum. Think of it like a barcode for the universe. Hydrogen, oxygen, carbon, iron, each one has a unique signature. When scientists spread out a comet's light through a spectrograph, they can read those signatures the same way a scanner reads a grocery code. It's one of the most elegant tricks in all of science. You don't need to touch the thing, you just have to look at it the right way. When astronomers turned their spectrographs toward 3I Atlas, they found the familiar fingerprints of common cometary materials: water vapor, carbon monoxide, carbon dioxide, and a few organic molecules. But there were oddities too. The ratios were off. The chemical balance didn't match what we see in comets from our own solar system. It was like tasting a dish you recognize but noticing that the spices are all wrong. That subtle difference is where the story gets fascinating. Every solar system has its own recipe, its own balance of temperature, radiation, and chemistry when planets and comets form. In ours, the outer regions were cold enough for water and carbon-based ices to freeze solid. But in a hotter or more metal-rich system, different compounds might dominate. So when 3I Atlas releases gas, it's basically exhaling the atmosphere of a star system we've never visited. It's alien weather in chemical form. Of course, spectroscopy isn't perfect, it's indirect and messy. Astronomers have to account for interference from Earth's atmosphere, from the sun's glare, and from the limitations of their instruments. The data has to be cleaned, calibrated, and compared against known samples. But even with all that noise, the message was clear enough. This comet didn't just come from somewhere else. It was made somewhere else. And that's the kind of discovery that reshapes how we see everything. Because now, instead of guessing what distant worlds might be made of, we're getting physical evidence from their construction zones. Each interstellar visitor is a sample return mission we didn't plan. The trick is recognizing it before it's gone. It also gives scientists a rare chance to test long-standing theories about the early universe. Many of the building blocks of life, amino acids, sugars, complex organics, are believed to form on icy dust grains in interstellar space. Comets act like delivery trucks, ferrying those molecules to young planets. If interstellar comets like 3I Atlas carry similar compounds, it strengthens the idea that the ingredients for life are common, maybe universal. And that's not a small idea. That's the kind of realization that shifts humanity's self-image. Life might not be a cosmic accident. It might be a byproduct of chemistry that repeats itself across the galaxy. But for all its grandeur, the process itself is beautifully mundane. Scientists literally collect light, often a few thousand photons at a time, and feed it into detectors that separate it into colors. They stare at those colors for hours, then analyze where tiny dips appear in the graph. Each dip corresponds to a missing wavelength, and that missing wavelength means an element has absorbed it. That's how we know there's sodium in a star, methane on a planet, or carbon dioxide in a comet tail. It's cosmic forensics at the speed of math. For 3I Atlas, those spectral lines told a story of cold birth and long travel. Its composition suggested it had spent millions of years in deep freeze, untouched by sunlight until now. Some of its ices had never even been heated above the temperature of liquid nitrogen. When it entered our solar system, that ancient ice began to vaporize for the first time since the comet formed, releasing material older than Earth itself. So when you look up at a comet, that faint fuzzy glow isn't just gas and dust. It's history turning into light. The molecules evaporating off 3I Atlas right now are the same ones that formed around a distant star long before humans existed. That's not something we can hold or measure directly, but through the language of light, we can read it. And in that sense, telescopes are our time machines. Every photon is a messenger, every spectrum a letter from somewhere too far to reach. 3I Atlas may be a traveler from another world, but its light, its chemical voice, is something we can hear loud and clear. For all the complexity of modern astronomy, sometimes it boils down to a simple truth. You don't have to go there to know what it's made of. You just have to listen to the light before it fades. You could think of a comet as a dirty snowball, but that phrase is almost too polite. It sounds like something you'd throw during a snow day, not an object that could wipe out a species if it hit the wrong planet. A comet is more like a frozen grenade, a fragile, volatile lump of ice, rock, and organic sludge that spends most of its life in deep space silence until it stumbles close to a star. Then, under sudden heat, it wakes up, starts hissing gas and dust, and transforms into one of the most beautiful and dangerous sights in the universe. To understand what makes 3I Atlas special, you need to understand how comets work. Let's start with the basics. At its core, every comet has a nucleus, a solid chunk of rock, metal, and frozen gases like water, carbon dioxide, methane, and ammonia. Most are only a few kilometers wide, but that's enough to pack a staggering amount of energy. When a comet drifts through the frigid outer reaches of space, that nucleus is stable, asleep. Temperatures can hover just a few degrees above absolute zero, cold enough that even nitrogen turns solid. Nothing moves. Nothing reacts. Then, as it approaches a star, sunlight begins to heat the surface. The frozen gases start to sublimate. That's when a solid turns directly into a gas without melting first. The gas bursts out through cracks and pores, carrying dust with it. This forms a glowing halo around the nucleus called the coma, which can be thousands of kilometers wide. From a distance, that's the bright head of the comet you see through a telescope. The coma isn't just decoration, it's a temporary atmosphere made of water vapor, carbon monoxide, and complex organic molecules, the building blocks of life, ironically drifting in a toxic cloud. Sunlight and solar wind push this material outward, forming the iconic tail, actually two tails, one of dust and one of charged gas. In that moment, the comet goes from being a cold rock to a living performance. It breathes, it sheds, it glows. And as it races around the sun, every second strips away a little more of its body until it's reduced again to a dark, frozen core. What's wild is that many comets we see today are older than the Earth itself. They were born from the leftovers of solar system formation, the bits and pieces that never made it into planets. Imagine the early sun surrounded by a swirling disk of gas and dust. Near the center, heat keeps things too warm for ice. Farther out, beyond what astronomers call the frost line, the temperatures drop and ices can survive. That's where comets were born. Tiny time capsules from the dawn of planetary creation. In our solar system, most comets live in two massive reservoirs, the Kuiper belt, just beyond Neptune, and the Oort cloud, an enormous sphere of icy debris stretching halfway to the next star. These regions are like celestial deep freezers, preserving the ingredients of the early solar system in pristine condition. Every time one of these icy bodies gets nudged by gravity, maybe from a passing star or a rogue planet, it tumbles inward, giving us a cometary show. But 3I Atlas? It didn't come from our freezer. It came from someone else's. That's what makes it revolutionary. Its ices, its dust, its chemistry, all of it was shaped around a completely different star, in conditions we can only imagine. Maybe its parent star was cooler, making different compounds freeze first. Maybe it was richer in metals or surrounded by exotic organics. The composition of a comet acts like a cosmic fingerprint, and Atlas's fingerprint doesn't match anything in our solar database. There's also something strangely personal about comets. They're the universe's original messengers. Ancient civilizations feared them, worshipped them, blamed them for everything from plagues to wars. In a way, they were right to be awed. A single comet impact could change the climate of a planet, strip away its atmosphere, or even seed it with the precursors of life. Modern science has stripped away the superstition, but kept the awe. When we study comets, we're not just learning about ice and rock, we're studying memory. These things remember what the solar system looked like 4.5 billion years ago. They carry the original recipe of creation, unedited. And because comets evaporate a little each time they pass near the sun, every close encounter is also a kind of death. Their trails are literally made of their own remains. When you see a comet glowing in the sky, you're watching an ancient traveler slowly burn itself away in exchange for a few moments of glory. 3I Atlas is doing exactly that right now, shedding alien dust into our solar wind, leaving a faint, invisible trail that will disperse long after it's gone. Some of that material will mix with our own interplanetary dust, maybe even fall to Earth one day as a microscopic grain trapped in our atmosphere. If that happens, you could technically say that a molecule from another star system landed here, a tiny drifting immigrant from another sun. That's the real magic of comets. They blur the boundaries between here and out there, between creation and destruction, between the beginning of time and the present moment. We call them dirty snowballs, but that's a lazy nickname. They're fossils that move, time machines that melt. They carry the story of their birth in every atom, and for a few brief weeks as they race past our sun, they let us read the first chapter of a story we're still trying to finish. 3I Atlas isn't just another comet. It's a foreign archive, a library written in ice and dust, making one quick stop on its way through eternity. Let's take a mental step back, way back, and picture 3I Atlas before it ever crossed paths with our sun. Forget telescopes and comas and tails. Back then, it wasn't a spectacle. It was just a chunk of frozen debris orbiting quietly around some distant star. That's how all these interstellar wanderers begin, as leftovers. Every solar system forms from a swirling disk of gas and dust around a newborn star. Most of that material becomes planets, moons, and asteroids. But the outer edges, far from the warmth of the star, are too cold and too chaotic. There, countless icy rocks form and linger in the shadows, waiting to be forgotten. Sometimes, those quiet orbits don't stay quiet. A large planet migrates inward, disturbing the balance, or two stars pass close together, tugging on each other's debris fields with invisible hands. When that happens, chaos follows. One wrong gravitational nudge, and a comet gets ejected, flung out of its home system at escape velocity. That's probably how 3I Atlas began its voyage, as collateral damage from planetary billiards. It could have been orbiting its home star for billions of years before something disturbed it. Maybe a rogue planet, maybe a close-passing star, and sent it hurtling into interstellar space. Once that happened, it was on its own, forever. Space between stars isn't empty, it's just almost empty. There are stray atoms, magnetic fields, cosmic rays, all whispering around at near absolute zero. For a comet, that's a long, dark eternity. No sunlight, no heat, no motion except a slow, endless drift through a vacuum so still that time itself feels like it gave up. Think about that. 3I Atlas has probably been traveling for millions, maybe even hundreds of millions of years. While Earth's continents were still merging, while dinosaurs were evolving, while humans hadn't even dreamed of existing, this lump of alien ice was already adrift, moving silently between stars. It wouldn't have seen much, at least not in the way we think of seeing, but it would have felt things, the distant pull of gravity from stars it passed, the faint pressure of cosmic radiation, the rare collision with a dust grain traveling at tens of kilometers per second. Its surface would have been bombarded by interstellar particles, gradually eroding, darkening, hardening into a kind of protective crust. That's why many comets appear blacker than coal. Their surfaces are baked by cosmic radiation, turning once bright ice into tar-like carbon compounds. It's not romantic, but it's real. Interstellar travel is not a sleek spaceship adventure. It's slow decay in near-permanent night, and yet through that endless darkness, Atlas kept going. Its speed, around 60,000 miles per hour relative to the sun, sounds fast, but on galactic scales it's nothing. It would take tens of thousands of years to travel a single light year, and there are trillions of light years worth of space between galaxies. The only reason we even noticed it is because we just happened to be in its path when it crossed through our neighborhood. You could call that coincidence, but space runs on coincidences. Gravity is the universe's slowest matchmaker. So here it comes, coasting through the void, dark as soot, frozen solid, carrying the ancient chemistry of another star system, until suddenly it starts to brighten. Not because it changes, but because the sun does what stars always do. It gets noticed. As Atlas approached the outer edge of our solar system, sunlight began to strike it for the first time in ages. The outer layers of ice started to warm, releasing faint gases, a whisper compared to what would come later. The coma formed. The tail followed, and for the first time in millions of years, this frozen drifter became something visible, a comet again. For astronomers, that moment is electric. It's like finding a message in a bottle that's been floating across oceans for millennia, finally washing up on shore. Except this bottle was moving at interstellar speeds and glowing like a miniature star. And the best part? It's not staying. Once Atlas loops around our sun, it'll be gone again. Forever. Its trajectory is hyperbolic, which means gravity won't capture it. There's no round trip, no orbit, no coming back in a few thousand years like Halley's Comet. It's a one-time visit, a straight shot through our solar system and back out into the black. It'll leave our sun's influence behind, drift through the Oort cloud, and then cross into interstellar space again. A long, lonely journey that might last until the end of the Milky Way itself. Maybe one day it'll pass near another star, and someone else's telescopes will catch a faint blur of light and wonder the same things we're wondering now. That's the strange comfort of it. 3I Atlas isn't really ours. It doesn't belong to any system or star. It's a citizen of the galaxy, an unplanned traveler, a reminder that even the most stable worlds are built from chaos and luck. And as it fades from our view, it'll take with it a tiny piece of our story. Because now, for better or worse, our sun's light has touched it. Our photons have bounced off its alien ice and scattered into space. Somewhere out there, long after we're gone, that reflected light will still be traveling, a faint echo saying, "We were here too." By the time 3I Atlas reached the inner solar system, it had already traveled longer and farther than anything we can really imagine. But now, it was approaching something it hadn't felt in perhaps hundreds of millions of years: real heat. The sun isn't gentle to comets. It's a cosmic interrogation lamp. And when a frozen traveler like Atlas wanders too close, every secret it's been keeping gets burned out into the open. At first, the warming is slow. Ice that's been solid for eons begins to tremble and crack. Microscopic fissures open in the surface, venting gas at hundreds of meters per second. The faint haze surrounding the comet, the coma, balloons outward as sunlight hammers it from all sides. The coma can grow to be tens of thousands of kilometers wide, even though the comet's nucleus itself is barely a speck compared to a city. Then the real fireworks begin. As Atlas closes in on the sun, temperatures rise, and the chemical chaos ramps up. Some of the comet's ices, things like carbon dioxide and ammonia, sublimate early, but others, like water ice, only really start to erupt when the comet passes inside the orbit of Mars. That's when it begins to glow, literally. Sunlight reflects off the dust and gas in the coma, making the comet visible to telescopes and sometimes to the naked eye. At this stage, a comet becomes a living physics experiment. Its gases and dust are constantly being reshaped by solar radiation and magnetic fields. The sun's wind, a stream of charged particles moving at hundreds of kilometers per second, sweeps over it, bending and twisting its ion tail like a windsock in a storm. Every photograph is a new configuration, a snapshot of cosmic turbulence. 3I Atlas was particularly dramatic because of its trajectory. Unlike most comets that enter the solar system on predictable, often repeating paths, Atlas came in hot, a steep, plunging arc around the sun. That meant it was moving faster and experiencing more heat than most of the comets we've studied up close. And that, of course, made astronomers nervous. When a comet passes too close to the sun, it risks disintegration, a fancy way of saying it blows itself apart. The heat can vaporize so much of its mass that the nucleus loses structural integrity and breaks into fragments. We've seen this before. Comets splitting like fragile snowballs under stress, leaving behind ghostly trails of dust that slowly fade. For weeks, observers around the world watched to see if 3I Atlas would hold itself together. Its brightness fluctuated wildly, sometimes dimming, sometimes brightening again, as if the comet couldn't decide whether to survive or self-destruct. That inconsistency told scientists that something inside it was cracking. The gases escaping from the surface were pushing and pulling in uneven bursts, like steam leaking through fractures in a pressure cooker. Sure enough, as it neared its closest approach to the sun, what astronomers call perihelion, telescopes picked up the signs. The nucleus of Atlas began to fragment, tiny pieces, then larger ones breaking away from the core. Each fragment developed its own miniature tail, all fanning out like a shredded flag. To the human eye, that might sound tragic, but to scientists, it was gold. When a comet breaks apart, it exposes its inner layers, material that's been sealed off since the dawn of its formation. It's the difference between studying the surface of a planet and suddenly getting to look inside. For a brief window, we could see the raw composition of an interstellar object in ways that would never have been possible otherwise. Spectroscopic data from this period showed spikes in specific molecules: water, carbon monoxide, formaldehyde, even traces of cyanide compounds. These are the kinds of ingredients thought to play a role in the chemistry of life. And though the fragments of Atlas were doomed, they told us something invaluable. The same chemical foundations exist far beyond our solar system. That's the beauty of destruction in astronomy. Things die spectacularly, and in doing so, they teach us what they were made of. As the fragments of Atlas rounded the sun, they scattered and faded. Some vaporized completely. Others drifted into long, faint trails that blended with the solar wind. Eventually, all that was left was a thin, invisible stream of dust orbiting in roughly the same path. Over time, even that will disperse, perhaps seeding the interplanetary medium with a few alien molecules that will one day end up in a meteor, or even in the atmosphere of Earth. In that sense, the comet's destruction wasn't really an ending. It was an exchange, a bit of one star system becoming part of another. And for scientists, the aftermath was just as fascinating as the event itself. Instruments detected faint variations in solar wind behavior near the comet's path, a sign that its charged particles had briefly tangled with our sun's magnetic field. It wasn't dramatic enough to affect Earth, but it left a measurable blip in the sun's plasma data, proof that even a visitor as small as a comet can leave fingerprints on the solar system's largest player. After that, 3I Atlas continued its outbound journey, dimmer but not gone. The surviving fragments kept drifting outward, cooling rapidly as they moved away from the sun. Within months, they returned to the cold silence of space, fractured, faded, but still traveling. And just like that, the spectacle was over. But for the astronomers who had stayed up nights tracking every flicker and flare, it was a reminder of what makes science thrilling. You never get to keep what you study. You only get to watch it long enough to learn something before it's gone. Atlas had come from the void, burned briefly in our sky, and left behind just enough clues to make us question what else might be out there, waiting, drifting on its way. When a comet dies, it doesn't really disappear. It just changes form. It's one of the rare moments where astronomy starts to sound like philosophy. Nothing in space ever truly ends. It just drifts into something else. After 3I Atlas broke apart near the sun, its fragments began to spread along its orbit, forming a debris trail, a faint, invisible ribbon of dust, ice, and rock stretching millions of kilometers through space. To the naked eye, it's nothing, but to astronomers, it's the comet's ghost, still haunting the path it once blazed. These trails are how meteor showers are born. When Earth's orbit happens to cross one of them, those leftover particles slam into our atmosphere at tens of kilometers per second, burning up in streaks of light we call shooting stars. Every meteor shower, the Perseids, Leonids, Geminids, is basically a graveyard for an old comet, still giving us a light show long after the original object disintegrated. But here's the twist. 3I Atlas wasn't from our solar system. Its orbit is hyperbolic, meaning it's not coming back. Its debris trail isn't circling the sun, it's leaving. Those dust grains won't loop around to form a meteor shower here. They'll drift farther and farther outward until they're back in interstellar space, joining the endless cloud of dust that fills the galaxy. That's not poetic exaggeration. The Milky Way is literally made of this stuff. Every star system sheds debris. Every comet, asteroid, and collision adds a little more to the interstellar medium, the vast soup of atoms, molecules, and dust that floats between stars. Over billions of years, that dust becomes the raw material for new systems, new planets, and new comets. It's cosmic recycling on a scale that makes our human version look like amateur hour. So when 3I Atlas came apart, it didn't vanish. It donated. Each tiny particle that broke off carried the chemical fingerprint of its home system. Those atoms, maybe carbon, silicon, water, or nitrogen, are now drifting through the solar system at escape velocity. Some of them will cross paths with the outer planets. A few might get caught in Jupiter's magnetic field for a while before being flung back out, and a microscopic handful might even find their way to Earth, falling quietly through our atmosphere as invisible cosmic dust. That dust is valuable, literally priceless. Every year, hundreds of tons of interplanetary dust settle onto our planet, grains that were born before our sun even existed. Some of them land in the ocean, sink, and are buried in sediment for millions of years. Others fall in places like Antarctica, where they're preserved in ice. When scientists collect them, they find a chemical time capsule, complex organic molecules, amino acids, and carbon compounds that hint at the ingredients for life. That's why the debris from 3I Atlas matters so much. If even a few of its grains survive the journey and eventually reach Earth, they could tell us what chemistry was happening around another star billions of years ago. That's not just trivia. That's data on alien biology before biology even existed. There's also the question of what happens to all this debris once it leaves the sun's influence. It doesn't just vanish into an infinite void, it becomes part of the galactic dust cycle. Over time, radiation from nearby stars alters it, heating, ionizing, and breaking apart molecules. Cosmic rays change the chemical structure of ices and organics, turning them into more complex compounds like tholins, reddish polymers that might explain the strange colors of distant worlds like Pluto and Titan. Those tholins, by the way, are suspected to be a key step toward prebiotic chemistry, the kind of complex carbon chains that can evolve into amino acids, sugars, and eventually life. So, in a beautifully ironic twist, when a comet dies, it might be seeding the next generation of living worlds. Every fragment is a traveler, carrying microscopic blueprints for what might become something greater billions of years later. And if you zoom out far enough, past the orbits, past the solar system, past the spiral arms of the galaxy, that debris starts to look like veins of raw material connecting everything. Each comet, asteroid, and planet is just a temporary clump in a much larger cycle of matter. Life, when it happens, is simply what the dust does when given enough time and warmth. So yes, 3I Atlas is gone. It burned itself apart for a brief cosmic moment, and now it's dust. But that dust isn't lost. Somewhere, a few atoms from that alien ice are already mixing with ours. Maybe they'll end up in a future comet, maybe in a planet, maybe even in a living thing. And in that way, every comet that dies doesn't really disappear. It just changes audience. It stops being something you can see in the sky and becomes part of everything else you'll ever know. If you picture space as a vast, empty nothingness, you're not wrong, but you're also missing the best part. The emptiness isn't uniform, it's textured, woven. Like the ocean, it has currents, not of water, but of gravity. And those invisible currents are what carry things like 3I Atlas across the galaxy. Interstellar travel, for a rock or comet, isn't about propulsion or engines. It's about luck, momentum, and the constant pull and tug of stars playing catch with matter. The galaxy is full of gravitational traps and escape ramps, each one bending the paths of wayward objects ever so slightly. It's chaotic, but it's not random. There's a rhythm to it, a slow cosmic ballet choreographed by gravity itself. To understand how a comet from another star ends up in our sky, imagine the Milky Way as a giant pinball machine. Every star is a bumper, every passing planet a nudge. The comet starts off orbiting its home star, maybe in that system's version of the Oort cloud, a distant halo of icy bodies. Then, something disturbs it, maybe a nearby supernova, maybe a star passing too close, or maybe a rogue planet the size of Neptune cruising by like it owns the place. That's all it takes. A little gravitational shove, and the comet is ejected, launched out of its home system at tens of kilometers per second. Once that happens, it's free. No longer bound by any star's gravity, it joins the endless river of objects drifting between systems. But here's where it gets fascinating. Space isn't flat. The gravity of the Milky Way itself curves and channels these trajectories. Every star moves through the galaxy in its own orbit, dragging its debris field along. Sometimes two of those fields overlap. Sometimes a rogue object like 3I Atlas passes close enough to one star to get deflected toward another. Over billions of years, this creates an invisible web of gravitational highways, paths that link solar systems together in slow motion. Our solar system sits in one of those intersections. We're not an isolated island, we're a rest stop on a galactic highway of ice, rock, and dust. Most of the time, that traffic passes unseen, but every once in a while, a bright traveler catches the sunlight, and for a few weeks, we get a glimpse of the flow we're part of. 3I Atlas is one of those travelers. Its velocity and trajectory tell us it came from far beyond the reach of the sun, possibly the outer disk of the galaxy, where stars are sparse and cold. Its approach vector suggests it wasn't just wandering aimlessly. It had a history of gravitational encounters, like a passport stamped by multiple systems on its way here. That's one of the most mind-blowing parts of all this. Every interstellar object carries gravitational memory. Its path tells us where it's been deflected, how fast it's been traveling, and even hints at the mass and motion of stars it's passed. By tracing 3I Atlas's trajectory backward, astronomers can estimate where in the galaxy it might have originated. Though the farther you go, the blurrier the data gets. Still, some models suggest it could have been ejected from a binary system, two stars orbiting each other, where gravitational interactions are notoriously violent. Think of it like this. Binary stars are cosmic slingshots. If a comet passes close to one, it can get whipped around and thrown out at high speed, much like a spacecraft using a planetary flyby to gain velocity. That could explain why 3I Atlas is moving so fast, around 60 kilometers per second relative to the sun. That's way faster than anything naturally bound to our star. It also means 3I Atlas might not be the only one. For every interstellar comet we spot, there are likely millions more passing silently through the outer regions of our solar system, too small or too dark to see. These are the background travelers of the galaxy, an unseen population linking every star system together through a slow, shared migration of debris. In a sense, they're the connective tissue of the Milky Way. Stars form, live, and die. But comets and asteroids keep wandering, carrying the chemical DNA of their origins from one region to another. Over billions of years, that steady trade may have mixed the ingredients for life all across the galaxy. That's not just speculation, it's a theory called panspermia. And while it sounds like science fiction, it's rooted in chemistry. If molecules essential to life can survive the cold and radiation of interstellar space, and some experiments suggest they can, then every comet like 3I Atlas might be a courier, delivering the seeds of biology from one world to another. So when we watch an interstellar comet drift past, we're not just seeing a ball of ice. We're seeing a messenger from another chemical ecosystem, possibly carrying hints of how life started elsewhere, or even how it started here. It's also humbling to realize how small our solar system is in this context. From our perspective, the sun dominates everything, but on the galactic scale, it's just another streetlight along the route. For 3I Atlas, our entire solar system was a brief detour, a single curve on a highway it's been following for eons. It entered from one side, flared brightly for a few months, and is now already heading for the next. And that's what makes these interstellar visitors so haunting. They remind us that while planets and stars think in billions of years, comets think in journeys. 3I Atlas doesn't belong to any system or story. It's just passing through. One bright ancient hitchhiker on the Milky Way's never-ending road. Spotting something like 3I Atlas isn't easy. In fact, it's a little like trying to notice a single grain of sand flying through a stadium at midnight from across town while everything's moving. The only reason we even saw it is because humanity has gotten really good at watching the darkness. For centuries, comets were found the old-fashioned way. Someone with good eyesight, bad sleep habits, and a telescope pointed at the right patch of sky. The early comet hunters, people like Charles Messier, Caroline Herschel, and Edmund Halley, kept meticulous records, scanning the heavens night after night for tiny lights that moved against the background of stars. Back then, the only detection algorithm was the human brain. But the universe doesn't make things easy. A comet can be fainter than the dimmest stars, move unpredictably, and only appear for a few weeks before fading forever. Now imagine trying to spot one that's not even from here, one that appears at a weird angle, moving way too fast with no orbital pattern to predict. That's the challenge astronomers faced with objects like Oumuamua and 3I Atlas. The key to finding them lies in technology, specifically in a network of wide-field survey telescopes that scan the entire sky every night, looking for anything that moves. That's how Atlas was found, by a system literally named ATLAS, short for Asteroid Terrestrial Impact Last Alert System. Ironically perfect, it was built to detect asteroids that might hit Earth, but instead, it found something that had no intention of staying. Here's how it works. The ATLAS project consists of several telescopes located in Hawaii, Chile, and South Africa. Every night, they photograph huge swaths of the sky, capturing millions of stars in each frame. Specialized software then compares these images with previous ones, pixel by pixel, looking for anything that has changed, a dot that's shifted position, brightened, or dimmed. Most of those moving dots turn out to be near-Earth asteroids, satellites, or camera artifacts, but once in a while something moves in a way that doesn't make sense. Too fast, too angled, too hyperbolic. That's when astronomers start paying attention. When 3I Atlas was first spotted in early 2024, its motion immediately stood out. It was moving faster than anything bound by the sun's gravity. Its orbit calculations showed a clear hyperbolic path, meaning it wasn't coming from anywhere in the solar system, and it wasn't going to stay. Within days, observatories around the world were tracking it, confirming what everyone hoped, but hardly dared to say. It was interstellar. That word alone, interstellar, still sends a thrill through every astronomer who says it out loud, because it means you're looking at something born around another sun, something that doesn't belong here. The tools that make this kind of discovery possible are absurdly precise. Modern sky surveys use CCD cameras capable of detecting light so faint it's equivalent to seeing a candle flame on the moon. They generate terabytes of data every night, which gets processed by machine learning algorithms trained to spot movement patterns that match potential asteroids or comets. But software alone isn't enough. Once a candidate is found, human astronomers step in, checking trajectories, verifying images, cross-referencing other observatories' data. Within hours, messages ripple through the global astronomy community. Possible interstellar object detected. Then begins the race. Because the moment an interstellar object enters our solar system, the clock starts ticking. It's moving fast, sometimes 60 kilometers per second or more, and in a matter of weeks, it'll be gone forever. Every telescope that can swing in its direction does. The goal is to gather as much data as possible before it fades below detectability. In the case of 3I Atlas, researchers coordinated across continents. The Very Large Telescope in Chile, the Hubble Space Telescope, and countless smaller observatories joined forces, capturing images, spectra, and light curves. Amateur astronomers, too, pointed their backyard scopes skyward, hoping to catch a faint smudge of light, not because they'd see much, but because they could say, "I saw an alien comet." The next step is refinement. Once the raw data is collected, computers crunch the numbers, measuring how the object's position changes night by night. From that, scientists can determine its speed, direction in, and orbit with astonishing accuracy. When those calculations show a hyperbolic orbit, an open curve instead of a closed ellipse, that's the smoking gun. It means this thing isn't coming back. And with that realization, the object graduates from being a comet or asteroid to something far rarer, an interstellar visitor. The technology is only getting better. In the next few years, the Vera Rubin Observatory in Chile will come online, a game changer for astronomy. It will scan the entire visible sky every few nights, capturing 20 terabytes of images each night with a 3.2 gigapixel camera. That means future Oumuamuas and ATLASES won't slip by unnoticed. We might even catch one early enough to send a probe after it. And that's not science fiction. NASA is already studying concepts for interstellar interceptors, spacecraft designed to wait in orbit, ready to launch the moment a new interstellar object is detected. The idea is to chase it down before it's gone, take measurements up close, maybe even grab a sample. Think about that for a second. A mission not to another planet, not even to another star, but to a visitor from one. That's the direction this field is heading, from luck to precision, from discovery to pursuit. The irony is that for all our advanced tools, it still comes down to timing. We live in a universe filled with travelers, but they're small, fast, and brief. If you blink, or in this case, if your telescope blinks, you miss them. So when we catch one, even for a few nights, it feels like the cosmos is letting us peek behind the curtain, a glimpse at the traffic moving between worlds, proof that space isn't silent, it's alive with motion. And the fact that we can detect that motion from millions of kilometers away through instruments built by people who once thought stars were fixed might be the most astonishing part of all. When Oumuamua flew by in 2017, it was gone before we even knew what it was. By the time the scientific community realized it wasn't a normal asteroid, it was already speeding out of the solar system to too far, too fast, and too mysterious. That stung. The same story repeated with 2I/Borisov in 2019, and again with 3I Atlas in 2024. We keep seeing these interstellar guests waving from the cosmic highway, and we never get close enough to say hello. NASA and ESA have decided that's not going to happen again. Enter the Interstellar Probe Interceptor, an ambitious idea that sounds like science fiction but is inching toward reality. The mission concept is simple in theory and borderline insane in execution. Park a spacecraft somewhere in deep space, keep it powered and waiting, and when the next interstellar object is detected, launch it like a bullet. You see, the problem isn't finding these objects anymore, it's catching them in time. They move at tens of kilometers per second, and they're usually discovered only weeks or months before they swing past the sun and vanish forever. Designing a probe that can react that fast is like trying to sprint after a car going 150 miles per hour, but in 3 dimensions and without air to push against. NASA's solution is a mission called the Interstellar Object Explorer, IOE, a conceptual descendant of the Comet interceptor mission being developed by the European Space Agency. The plan: build a spacecraft and park it near the L2 Lagrange point, a gravitational sweet spot about 1.5 million kilometers from Earth, where it can just sit there, waiting, with minimal fuel use. When telescopes detect a new interstellar visitor, say something like 3I Atlas, the interceptor would wake up, calculate a trajectory, and fire its engines to go chase the intruder. It wouldn't just watch from afar, it would intercept the object mid-flight and collect data up close. Ideally, it would take high-resolution images, analyze gas and dust emissions, and maybe even fly through the coma, that glowing halo of material that forms when comets heat up near the sun. And if it gets really lucky, it might grab a few particles in a special collection shield, tiny fragments of another star system, frozen in time. Material that was born around an alien sun billions of years ago, finally being touched by human hands. Let's not understate this. That would be one of the biggest scientific milestones in history. A rock from another solar system isn't just a curiosity, it's a sample of another chemical environment. It could tell us how different stars form their planets, how common certain elements are, and whether the building blocks of life, amino acids, carbon chains, complex organics, exist everywhere or are unique to our little corner. It's one thing to look at exoplanets through telescopes. It's another to physically hold a piece of one's leftovers. The problem, of course, is speed. These things move faster than any spacecraft humanity has ever built. Oumuamua was going around 87 kilometers per second. Even Voyager 1, our fastest and farthest probe, would look like a tortoise in comparison. To catch an object like that, you need something powerful, efficient, and quick to launch on short notice. That's why scientists are eyeing solar sails, giant reflective sheets that use sunlight as propulsion. It's elegant. The closer to the sun you deploy it, the more powerful the push. Some designs propose using a solar Oberth maneuver, where a spacecraft dives dangerously close to the sun, uses the gravity and heat to boost its velocity, then flings itself outward like a slingshot. It's risky. Think frying an egg on your spaceship risky, but it could reach speeds no chemical rocket could dream of. Others have proposed ion propulsion, like the kind used on NASA's Dawn and Deep Space One missions. Instead of burning fuel in bursts, it uses electricity to accelerate ions continuously, providing a steady push for months or years. It's slower to start, but over time it can reach incredible speeds, perfect for chasing something that's already halfway to the edge of the solar system. Then there's the wildcard option, laser propulsion. The concept comes from Breakthrough Starshot, a project backed by Stephen Hawking before his death. The idea is to use ground-based lasers to accelerate tiny probes to a fraction of the speed of light. For interstellar chases, a scaled-down version might one day allow us to fire a lightweight, high-speed interceptor toward a passing object almost instantly. No matter the method, the philosophy is the same. We can't predict when the next interstellar visitor will arrive, but we can be ready. The first serious step in that direction will be ESA's Comet interceptor, launching later this decade. While it's not specifically designed for interstellar objects, it's a proof of concept. It'll wait at the L2 point, just like the planned interstellar probe would, and once a new long-period comet is detected entering the inner solar system, it'll pounce. If that comet happens to turn out interstellar, all the better. These missions are teaching us something profound. Readiness is everything. The universe doesn't operate on our schedule. We can't plan an interstellar encounter years in advance. We can only stay alert, Instruments primed, engines warmed, ready to chase whatever wanders in. It's a strange feeling, waiting in the dark for something unknown, something not from here. But that's exactly what space exploration has always been. Every great discovery in astronomy has come from paying attention to the unexpected. When the next 3-eye atlas streaks by, we might finally be ready to meet it halfway, to capture the first close-up glimpse of a traveler from another sun. And when that happens, it won't just be a scientific event. It'll be a moment of connection, proof that our tiny world is part of a much larger network of systems, exchanging material, sharing chemistry, and maybe, someday, sharing life. The galaxy isn't empty. It's full of motion. We've just been too slow to catch up, until now. Let's start with a bold truth. Every rock, every drop of water, every molecule in your body has likely been somewhere else before. The carbon in your cells, the calcium in your bones, the iron in your blood, all forged in ancient stars long dead. We're walking archives of cosmic recycling, so when we study something like 3-eye atlas, what we're really doing is looking into another chapter of the same story, just written in a different solar system. The real treasure of an interstellar object isn't its shape or orbit, it's its chemistry. If you can figure out what it's made of, you get a glimpse of how other star systems cook their planets, their comets, and maybe even their life. That's where spectroscopy comes in. It's the cosmic version of CSI. When sunlight hits an object like 3-eye atlas, some wavelengths are absorbed by the chemicals on its surface, leaving behind a signature, a set of dark lines in the light spectrum. Each molecule leaves a different fingerprint. Compare those fingerprints to the ones we know, and you can tell if something's made of water ice, carbon compounds, methane, ammonia, or complex organics. When scientists analyzed the spectra of 2I/Borisov back in 2019, they found something fascinating. It looked chemically familiar. It had cyanide gas, carbon dioxide, and diatomic carbon, the same building blocks found in comets from our own solar system. In other words, chemistry doesn't seem to care where you are. The universe tends to make the same ingredients over and over again. That alone is huge. It means the raw materials for life, hydrogen, carbon, nitrogen, oxygen, aren't special to us. They're universal. Wherever stars form, so do these molecules. It's like the galaxy is using the same recipe, just with different ovens. But the most interesting question is what happens when those ingredients start hitchhiking. Enter the theory of panspermia, the idea that life, or at least its essential components, can travel between worlds. The concept sounds wild, but it's got real scientific legs. If microbes, amino acids, or even prebiotic molecules can survive the cold and radiation of space, they might be carried on asteroids, comets, or interstellar dust, shot across light years, landing on newborn planets and seeding them with the ingredients of biology. And that's where interstellar objects like 3-eye atlas become more than curiosities. They become test cases. If we could sample one directly, we could find out whether its chemistry stops at simple organics or crosses into something more complex, something that looks like the precursors to life as we know it. We already have some clues that the universe likes to make these complex molecules. In 2023, astronomers using the ALMA telescope in Chile found amino acid precursors, molecules that lead to the formation of amino acids in the disk of gas and dust around a young star called IRAS 16293-2422. And here's the kicker. Those same kinds of molecules have been found in meteorites that landed on Earth. That's two completely different places, light years apart, producing the same biochemical signatures. You don't need to be a romantic to see the pattern forming. Life's chemistry might be as common as starlight. If 3-eye atlas, or any future interstellar visitor, contains those same compounds, it would strengthen the case that life isn't an Earth-only phenomenon. It would mean that somewhere out there, on another rocky world orbiting another star, the same chemical dance could be happening, or already has. And it gets even stranger. Some researchers propose that Earth itself might be a beneficiary of interstellar chemistry. The early solar system was chaotic, full of impacts, comets, and collisions. It's entirely possible that an object like 3I Atlas delivered crucial organic molecules billions of years ago, helping to kickstart biology on our young planet. In other words, maybe we owe our existence to a passing visitor like the one we're studying now. That idea is both poetic and unsettling. It means life could be the universe's default behavior, something that happens naturally when enough chemistry is left alone for long enough. The line between alive and not alive starts to blur when the ingredients are everywhere and the conditions repeat across billions of worlds. And there's another layer to this. If life can spread between systems, then interstellar visitors aren't just scientific opportunities, they're time capsules. Each one could carry the chemical signature of its home system, preserved for billions of years. Studying enough of them might let us map the galactic distribution of life's potential, a chemical census of the Milky Way. Imagine a future where we've analyzed 10 or 20 of these visitors and start to see patterns. Maybe some come from carbon-rich systems where complex molecules thrive. Maybe others are barren, forged in metallic regions of the galaxy where organic chemistry never caught on. Piece by piece, we'd start to see which parts of the Milky Way are most likely to host life, and which are cosmic deserts. That's the kind of knowledge that rewrites philosophy books, not just science papers. Of course, getting that data means actually touching one of these things, something we've never done. But missions like the Interstellar Probe or ESA's Comet Interceptor might finally give us that chance. A sample from an alien comet could confirm what's been suspected for decades, that life's ingredients aren't confined to one tiny blue dot, but are drifting freely between the stars. And if that's true, the next logical question follows naturally. The one everyone secretly hopes the data will answer. If life's ingredients are everywhere, then where's the life itself? If you want to understand the search for alien life, you need to start by accepting one hard truth. We don't actually know what life looks like. We have one data point, Earth, and everything else is speculation wearing a lab coat. We assume life means carbon, water, warmth, oxygen, and sunlight, because that's what we need. But what if that's just our version of the story? That's where interstellar visitors like 3I Atlas kick open the door. They're not from around here, literally, and that means they carry chemistry from a completely different set of cosmic circumstances, different star type, different planetary formation history, maybe even different definitions of what organic means. Studying them is like getting mail from another galaxy's biology department. To understand why this matters, we need to talk about biosignatures. These are the clues scientists look for when searching for life beyond Earth. Not little green men waving from Mars, but measurable evidence that something biological might be happening. On Earth, the biggest biosignatures are simple: oxygen in the air, methane from living things, and complex organic molecules that shouldn't form without biology's help. When telescopes like the James Webb Space Telescope, JWST, point at distant exoplanets, they look for exactly those fingerprints in the planet's atmosphere. The way light filters through during transits can reveal what gases are present. If a planet shows both oxygen and methane, that's suspicious, because those two gases destroy each other quickly unless something is constantly replenishing them. On Earth, that something is life. Now, interstellar visitors give us another way to search for those signs. They're like care packages from alien solar systems, full of frozen chemistry that's been traveling through space for millions of years. If one of them contains traces of amino acids, or something even more complex like lipid precursors, it suggests that those building blocks, and maybe life itself, aren't confined to one lucky planet. And here's where it gets philosophical. The discovery of even a single molecule that can only be made biologically, found inside an interstellar object, would immediately change our definition of alien life. It wouldn't matter if we never found a living organism. The chemistry alone would prove that biology happened somewhere else. Think about what that means. No message, no radio signal, no sci-fi drama. Just a frozen clue quietly drifting between stars, carrying the proof that we're not unique. It's not the cinematic revelation Hollywood promised, but it's more profound. It's the universe whispering, "You're not alone. You're just early." Of course, that's the optimistic side. The cautious side, the one wearing the safety goggles, knows there's a big difference between organic chemistry and life. Every comet we've ever studied, from Halley's to Rosetta's 67P, has shown organic molecules. But organic just means carbon-based. It doesn't mean living or even complex. You can make amino acids in a lab or in deep space with no biology required. Still, the deeper we look, the more the line blurs. In 2024, JWST detected a molecule called methenamine in the icy clouds of a forming star, a molecule that can lead to amino acids and sugars. These aren't rare events. They're happening across the galaxy all the time. The chemistry of life seems to be written into the universe's basic playbook. So if the building blocks are everywhere, what's stopping life from popping up all over the place? That question leads us to the most unsettling scientific riddle of all, the Fermi paradox. If life is common, where is everyone? One possibility is that life is common, but intelligent life, the kind that builds telescopes and podcasts about aliens, is incredibly rare. Maybe microbial life is the rule, not the exception. Maybe the galaxy is full of tiny, silent biospheres, each one bubbling away quietly, never evolving far enough to notice the others. Or maybe civilizations rise and fall faster than we can detect them, a cosmic game of whack-a-mole, where no one survives long enough to say hello. It's not the most cheerful theory, but it's one scientists take seriously. That's why interstellar visitors are so important. They don't need to talk. They don't need to survive. They just need to exist. Every one of them carries chemical evidence from its home system, like spores from another world drifting through the dark. And if even one of those spores shows a hint of life's handiwork, we'll finally know that the silence of the cosmos isn't emptiness. It's distance. And maybe, just maybe, that distance is shrinking. Because as our detection tools improve, we're starting to see the finer details of the galaxy's chemistry. We're mapping the distribution of organic molecules across star-forming regions, comets, and even the atmospheres of exoplanets. We're finding the same molecules everywhere. Formaldehyde, cyanide, methanol, acetylene, like recurring verses in a cosmic song. The melody is clear. The ingredients are universal. What we don't yet know is whether the recipe repeats the same way twice. When the next interstellar object appears, and it will, we might be ready not just to watch it pass, but to reach out and touch it, to bring back a piece of its home, analyze it atom by atom, and maybe find a molecule that whispers, "I was once alive." That single discovery would do what centuries of philosophy never could. It would end humanity's loneliness. Not because we'd found aliens, but because we'd proven that life, any life, is woven into the universe itself. Here's the thing about science. Once we see something amazing, we immediately want to see it again, closer, faster, and with more expensive equipment. Interstellar objects are no exception. Oumuamua lit the match in 2017. Borisov kept it burning in 2019, and 3I Atlas poured gasoline on the fire in 2024. The scientific world now has one collective thought: next time we catch one. So what does that actually mean? Let's start with the Vera C. Rubin Observatory, which is set to begin operations soon in Chile. This telescope is basically the night sky security camera, except instead of catching porch pirates, it catches comets, asteroids, and anything else that dares to move. Every few nights, it'll scan the entire visible sky, capturing images so detailed that if a new comet appears, even faintly, it'll be flagged within hours. The Rubin Observatory will be a game changer for interstellar research. Right now, we detect maybe one interstellar object every few years, mostly by luck. But with Rubin's massive data pipeline and lightning-fast processing, that number could jump to dozens per decade. That's enough for statistical science to actually compare origins, compositions, and trajectories instead of treating every object like a rare miracle. Once we can reliably spot these travelers, the next step is interception. NASA's Interstellar probe, currently in the conceptual phase, aims to be the farthest-reaching mission in human history. It would launch in the 2030s or 2040s and head outward, beyond the heliosphere, that protective bubble of solar wind that defines the edge of our solar system. Its goal? Study the interstellar medium directly, measure cosmic dust, and maybe, if we're lucky, encounter something that wandered in. There's also talk of a dedicated interstellar object interceptor, a nimble spacecraft designed to sit in standby orbit and pounce the moment a new visitor is spotted. Think of it as the cosmic equivalent of a Formula One car waiting at the starting line, fueled, ready, and just waiting for the signal. The mission's design would allow it to intercept the object within months, snap images, and possibly even sample its dust using a high-speed collector shield. These are not pie-in-the-sky dreams. NASA's Jet Propulsion Laboratory and ESA have both run feasibility studies. The challenge isn't the engineering, it's timing. You can build the fastest probe in history, but if you find your target too late, you're chasing a ghost. That's why missions like this depend so heavily on early detection, a perfect marriage of data science and raw rocket power. And that's where AI enters the picture. The amount of data modern telescopes produce is ridiculous, terabytes per night. Human astronomers can't sift through all of it, so machine learning does the heavy lifting. Algorithms trained to recognize motion, brightness changes, and orbital patterns can now flag anomalies faster than any human ever could. In a sense, the next interstellar discovery won't be made by an astronomer staring through a telescope. It'll be made by an AI script running at 3 MeV. Once flagged, human scientists will jump in, run orbital simulations, and confirm the trajectory. If it's interstellar, the clock starts ticking. A global scramble begins to coordinate telescopes, instruments, and, if possible, spacecraft. We're on the verge of turning what used to be serendipity into a systematic process. And here's where it gets really exciting. All this technology, the telescopes, the AI, the interceptors, is paving the way for something even bigger: interstellar sample return. Imagine this. A probe launches, intercepts a passing object, scoops up particles, and brings them back to Earth. Inside those grains might be molecules that formed around another star, preserved for billions of years in interstellar deep freeze. When those samples arrive, scientists could compare them directly to material from our own solar system, essentially holding up two fingerprints from different stars. If they match, we'd confirm that the same chemistry happens everywhere. If they don't, we'd have our first concrete proof that the universe builds worlds differently depending on where you are. That's not a dream for the distant future. The Comet Interceptor mission, launching later this decade, will be the first rehearsal. It's designed to rendezvous with a pristine comet entering the solar system for the first time, possibly even an interstellar one. The mission will deploy multiple spacecraft to study the comet from different angles, giving scientists a 3D understanding of its structure, gas emissions, and surface composition. Every success like that brings us one step closer to the ultimate goal: capturing an interstellar visitor in real time. But the future of interstellar science isn't just about hardware. It's also about mindset. For centuries, humanity's exploration was confined to our own solar system. The planets, their moons, the sun, that was our neighborhood. The idea of studying something from another star was as unthinkable as walking to the moon was in 1400. But now, the line between our system and theirs is blurring. The galaxy is starting to feel smaller, connected by these messengers drifting in and out. we're also learning to collaborate like never before. The discovery of 3I Atlas wasn't the triumph of a single telescope or nation. It was the result of dozens of observatories around the world working together in real time. The next generation of interstellar missions will be even more global. NASA, ESA, Japan's JAXA, and private companies all pooling resources to chase the same cosmic ghosts. It's no exaggeration to say we're entering the dawn of interstellar astronomy, the moment we stop just looking outward and start interacting with things that come from beyond our sun. And if the pattern continues, if Rubin, JWST, and the next generation of telescopes keep spotting more interstellar visitors, we might soon realize that our solar system isn't a quiet outpost at the edge of nowhere. It's a crossroad. The stars aren't far away. They're already sending us postcards. We just had to build the eyes to see them. Let's take a step back. For 15 parts, we've been chasing a rock, an icy, dusty, anonymous traveler from another star. We followed it through gravitational highways, past the sun, and back into the black. But somewhere along the way, the story stopped being about the comet. It became about us. Here's the quiet truth. Interstellar visitors are mirrors. They don't just tell us about where they came from, they tell us what kind of species bothers to notice them. Humanity, for all its noise and chaos, does something remarkable. We look at a streak of light, 300 million kilometers away, moving faster than any spacecraft we've ever built, and we decide to learn everything about it. That curiosity is our defining trait. The universe doesn't owe us answers, but we keep asking questions anyway. Every time an interstellar object enters our solar system, we don't see a threat or a mystery to fear. We see a chance to understand. That's rare. That's hope disguised as science. When Oumuamua was first detected, there were people who joked, half seriously, that it might be an alien probe. Others scoffed, but even that argument, that need to wonder, is what makes us who we are. We can't stop looking for meaning in the unknown, and in a universe this indifferent, that's practically a superpower. The deeper lesson of 3I Atlas isn't just in its trajectory or its composition, it's in the way the world reacted. Within hours of its discovery, telescopes on every continent were turning toward it. Amateur astronomers shared coordinates. Scientists collaborated across time zones. For a brief moment, the planet acted like one organism. Eyes pointed at the same point in the dark. That's what exploration does. It unites us not through politics or culture, but through perspective. When you're studying something that came from another star system, your national borders start to look small. You realize that Earth, with all its oceans, mountains, and arguments, is just one speck in a vast neighborhood. And yet, against all odds, that speck built machines that can see 1 trillion miles away. It's hard not to feel humbled by that. We spend most of our lives focused inward. Deadlines, traffic, screens, the usual human mess. But every once in a while, something drifts through our corner of the galaxy, silent, ancient, indifferent. And for a brief moment, we remember how big everything really is. There's also a deeper comfort hidden in this cosmic chaos. If interstellar objects are common, then the galaxy is constantly exchanging material. Bits of one world becoming part of another. The same dust that formed the sun might someday drift into another system and form a new planet. The same atoms that once belonged to another star might be flowing through your bloodstream right now. We are, quite literally, made of the universe. And the universe keeps visiting itself through us. That's the poetry of science, the part that textbooks never quite capture. It's not just data or formulas, it's the realization that by studying the cosmos, we're studying our own reflection in a much larger mirror. Every comet we chase, every particle we analyze, every theory we test, it's all part of a single act of defiance against meaninglessness. Because when we look out there, we're really asking one question over and over. Are we alone? And the answer, even if it's never spoken, keeps getting louder with every discovery. No, we're not in the sense we used to mean. The universe is busy. It's full of chemistry, motion, structure, and potential. We might not have met our cosmic neighbors yet, but their fingerprints are everywhere. When the next interstellar visitor appears, we'll be ready. Not just with telescopes and spacecraft, but with context. We'll know that what we're seeing isn't just an object, but a messenger. A reminder that we live in a connected galaxy, one that trades material like stories around a campfire. And maybe, someday, when we finally send a probe to intercept one of these travelers, collect a sample, and hold a fragment of another star in our hands, we'll realize that the universe was never silent. It's been speaking all along. We just had to learn the language. That's what science really is, the slow discovery that we belong to something vast and alive. Interstellar objects don't just show us the universe. They show us the best parts of ourselves, the part that's curious, the part that reaches, the part that refuses to stop wondering, even when the answer is light years away. So as 3i Atlas fades back into darkness, maybe the right reaction isn't sadness or awe. Maybe it's gratitude. Gratitude that, in a universe of cold distances and ancient silences, we've managed to build a species that can look up, see something from another world, and whisper, "There you are."